From Europe, good evening. Got it. Good evening from Europe. My name is Marilena Pavel, and I will be chairing the session of our Transformative Vertical Flight meeting of today. I am placed in Delft, at Delft University of Technology, and I brought you today two guests from Finland. It is evening in Finland, so thank you for being with us. The presentation, it will be an interesting talk on the CONOP, which is related to the wildfire fighting. And I have at the moment Professor Fabrice Saffre and Mr. Hannu Karvonen from the from the Technical Research Center in Finland. I would like to say our group of Transformative Vertical Flight I think was founded in 1996. I work in this group since that moment, and our goal is to define the challenges and the roadmaps that we need in order to introduce advanced air mobility in the public services and make use of the new generations of airplanes. So I would like the speakers to introduce themselves first, because they can introduce themselves the best, and looking forward to your talk.
Thank you, Marilena. And I will start sharing now. Hope you can see it. So I'm Hannu Karvonen. I have been working at VTT for about 14 years now. So VTT is the Technical Research Center of Finland, and I work there as a senior scientist and project manager. And I actually have a human factors background from different safety critical environments, on which I finished my PhD also about 3 years ago. And currently I'm working mostly in many drone-related projects at VTT, especially with drone swarms. And yeah, just to let you know, our plan is that I will start with some slides about the topic, and then Fabrice will continue with his slides and some simulation demos, and maybe Fabrice, you will introduce yourself then. So
yes, that's the plan.
All right. So this presentation is related to a recent concept of operation study that we have conducted about a design of a future drone swarm solution to support the wildfire management here in Finland in a project called FireMan. And here's first shortly just some basic info about the FireMan project. So the long name of the project is Unmanned Aerial Systems-Based Solutions for Real-Time Management of Wildfires. And the project is funded by the Academy of Finland, which is kind of like the National Science Foundation here. And we are now on our second year of the project, and the core research consortium who is receiving the funding includes the Finnish Geospatial Research Institute, who is the coordinator of the project, and then us at VTT and the universities of Oulu and Jyväskylä here in Finland. And there's also some collaborators there with their logos on the right, such as the Finnish UAV ecosystem. And in addition to those, we actually have around 30 authorities and companies as collaborators in the project who are working in the domain of wildfire response. So then brief intro to the topic of this presentation. So the phases of fighting wildfires include, on a very rough level, the prevention, the surveillance, and the suppressing efforts. And actually, different types of drones in general can greatly benefit all of these phases. For example, with their real-time situational awareness sensors that are flown in the air to detect, and once detect those fires, then can also monitor those fires. And it is no wonder, therefore, that currently here in Finland, for example, some fire brigades include a drone pilot. And well, I would say that a typical practice is that the pilot uses a single quadcopter within the line of sight in the place where the fire is occurring to monitor the situation from above and sort of providing the eyes in the sky. But in the future, it can be seen that both fixed wing and quadcopter drones could be operated beyond vision line of sight with much more automated solutions, including even some type of semi-autonomous swarms, which will be then supervised and controlled from a control center, possibly a bit further away from the actual scene of the fire. And then here's some background about the CONOP study that we conducted. So first, one definition, just to clarify things, so that you might know that there are like varying definitions of what a CONOPS is in different contexts, like in military or in aerospace management or etc. But especially from this complex software-intensive systems development perspective, one of its first definitions has been that a CONOPS is basically, or it contains the following elements mentioned there, and it includes this a description of the current system or situation, the justification for the nature for the proposed changes and the new features, and the operational concept for the new or modified system, and the operational scenarios also for that system, and a summary of organizational and operational impacts, and an analysis of the proposed new system as well. So the aim, I would say, in developing this kind of CONOPS is to just communicate the different quantitative and qualitative system characteristics to all stakeholders during the systems engineering, mostly in the beginning phases, but also it can be utilized in later phases of the development. And actually, in previous research, developing this kind of a CONOPS when designing complex socio-technical systems has shown really to be a useful approach and an integrative element for all stakeholders. So it has been shown, for example, to support this kind of cross-disciplinary communication of experts from various backgrounds during the systems engineering life cycle. And there's actually a ton of research done in regards to various types of CONOPSes and their usefulness for different purposes, but maybe I don't go into details of those here. But yeah, so even though a CONOPS is typically developed for some future system, typically, so before that, it is really necessary to understand the current operational practices. And to do that, in this FireMan project, we organized altogether 7 subject matter expert interviews here in Finland. And after those, we held also a large workshop with around 40 participants from relevant Finnish stakeholders, like, for example, the fire departments, the authorities, the companies, and research organizations. And the questions and themes of these interviews and the workshop was based actually on these human factors engineering approaches that we have developed. And yeah, I want to mention also that we have been also, participating in some of the controlled burning events here in Finland with our quadcopters in order to get this more like practical feel for the fire situation and how the drones can actually monitor the fire from different angles and how it's safe to fly the drones in that fire situation and so on. And I could actually show just a short video from those burnings now. So this is also a nice visit Finland and see the nature clip here. As you can see, we have a lot of beautiful forests and lakes here, and yeah, Finland is actually called the land of the 1,000 lakes. We didn't know. So there you can see some of our pilots from VTT. So as I mentioned, these are controlled burning events, and so no, they are not real wildfire. They are quite kind of rare here in Finland, but this is good practice for us. And you can see that there's a lot of smoke in the air. And if the fire is a large one, you can't really see anything through the smoke, except if you use this kind of infrared thermal imaging camera. You can see very clearly through the smoke where the fire front is actually advancing. But with the normal RGB video, you can't really see it. And Yeah, actually in this video, there's only a fraction of the material that we have gathered. So we have gathered quite a lot of RGB and thermal imaging camera video material from different burning events. And now we are using that material to train the AI, which is then ultimately used to automatically detect the fire and also estimate the propagation of the fire from during certain time intervals. Like, for example, where the fire is going to be in 5 minutes, 10 minutes, 15 minutes. So that is really useful information for the incident commander who is commanding the fire crews on the ground then. And the larger topics that we dealt in those interviews that we conducted on the workshop study, and they were related, for example, to these topics. So what specifically in Finland are, first of all, the current aerial forest fire surveillance practices, then secondly, the current main activities in wildfire management situation in a given scenario, then thirdly, the key actors or stakeholders and technology entities in a wildfire situation, and fourthly, also different challenges that have been identified in current quadcopter usage in wildfire situations. And finally, we also had a section where we focused on future vision regarding drone usage in wildfire situations. And yeah, perhaps I don't present the vast amount of information that we have regarding the current operational practices. I will just show one slide regarding that, and we will then go directly to the results regarding the future ConOps that we have developed. But here you can see the current operational practices for the certain scenario that we defined. So on the right, you can see an example of how we approach this kind of imaginary operational scenario, and the current practices which we went through with the experts. Don't worry, I'm not going to go into detail all of those, but you can see that there's a certain notation that we use for this that is based on approach called functional situation modeling, which we have been using previously in different types of analysis of operating practices, for example, in the nuclear power plant operations or emergency rescue. And yeah, it basically starts from the top and chronologically goes down during the different phases of the situation. Now, the situation or the point of this approach is that it connects the human actions that are done to the main purposes and critical functions that arise from the domain in question, which is fighting wildfires, basically in this case. And the human actions, they are depicted here and connected to these functions, which really need to be maintained all the time. And basically, in this way, we can understand what is the current human activity and how this future system could also support those critical functions of the domain and the situation in question. So this sort of worked as a basis for the ConOps. So here we will go more to the future ConOps side, which could be taken, let's say, in 10 years into use. And here we have in the as a animation high-level process description. I'm gonna show you guys soon. So this is still in the early stages, and it's a living document, but you can see that first, here we have, well, either a manned or unmanned aerial surveillance flight that detects a fire source somewhere in the environment. Well, this detection can also be done by human on the ground as well. But once that is done, there needs to be some sort of a detailed detection and analysis of the fire type. So, meaning, is it a real wildfire, or is it, for example, just somebody burning trash controllably? So basically, we have to have this kind of reconnaissance before alerting help. And for that purpose, we are planning to utilize a drone swarm here. It could be moved to the site and deployed to monitor the fire, if it's a real fire. And then help from the fire brigade would be alarmed. And the drone swarm would have these kind of different sensing capabilities on board, both of these fixed wing and quadcopter drones, and they would start monitoring the propagation of the wildfire from different angles. And also the fire brigade would then eventually arrive on the site and start the necessary operations. Now, from the drone swarms collected sensory information, this kind of real-time automated analysis of the situation would be conducted in a centralized AI system by modeling the fire and the terrain and predicting the fire's propagation between certain time intervals, like I mentioned. If not, no extinguishing will be done. And like I said earlier, we have been developing this AI solution already with the collected video training material here in Finland. And this kind of a solution would ultimately be kind of like a AI-based decision support that would help in the coordination of the extinguishing of the fire by the incident commander and the fire crews. So all these activities affect the behavior of the fire, as you know, and then that would be sort of looped back to the, or it would be sort of an automated closed loop behavior where the information that the swarm is collecting is affected by the actions what have been done based on the AI decision support. So yeah, and all this information is really presented in an intuitive and easily understandable way for the incident commander, who then commands and guides the fire crews and the extinguishing activities. And finally, at the end of this process, the fire would be extinguished, and with the help of this kind of a intelligent decision support. Now, maybe some of the related technical requirements for the swarm system here. So the system consists of a semi-autonomous swarm of both fixed-wing and rotary quadcopter drones, and the individual drones would have a flight time of, let's say, 1 hour, and they would be equipped with various kind of payloads, like, for example, RGB, thermal, hyperspectral cameras for different imaging purposes. And the station for the drone swarms, or the hive, one would say, for the launch is mobile, and it could be ordered by request to be delivered on wheels on the side of the fire. And the system would also include this kind of a swarm command, control, and communications platform, and a mobile control room through which the swarm's actions can be planned and coordinated. And in addition, a communication solutions based on 5G advanced or 6G ultimately would provide the sufficient bandwidth for high quality sensor feeds for different stakeholders that is needed. And I also want to mention here that some sort of a use-based solution or UTM solution for a safe airspace management of unmanned drones and manned aircraft. So there would be like helicopters and small planes, also like Cessnas, in the same airspace along with the unmanned drones. So we need to have some sort of a airspace UTM system here also inside. Then just to mention that from the human factors and organizational perspective, some main stakeholders in this ConOps include the relevant public authorities like fire and rescue departments, who take really the responsibility of organizing the drone swarm-based fire monitoring operation and the related C3 center. And naturally, cooperation with other authorities like the police and others is relevant here. And also with here in Finland, for example, with the aerial surveillance flight operators, with the voluntary fire brigades, telecom operators, the Meteorological Institute, they all play a really important role here. Now, as this study is more from the human factors engineering perspective, here you will see sort of the human operators that we have envisioned for the command, control, and communication center. So first of all, we have the swarm operator, for example, who communicates obviously with the other see-through human operators to really plan and supervise and end the drone swarm mission. And secondly, he also prepares and activates the swarm launches and plans the swarm's return to the launch pad. And Thirdly, also monitors the performance of the drone swarm. And fourth, also supervises coordinates and possibly also intervenes to the semi-autonomous drone swarms flying in the air. Then there's another human role called the data analyst, who basically analyzes the provided sensor analytics from the drones of the swarm. And he also monitors the overall wildfire situation and uses these AI tools or AI analytic systems to make this kind of refined analysis of the situation or recommendations for action for the incident commander. And yeah, he also obviously communicates with other stakeholders about the fire situation. And finally, there's also the U-Space or UTM operator who monitors and controls the airspace in that area. So this human operator basically establishes a U-Space area for the manned and unmanned aviation in that airspace and manages that. So yeah, obviously that needs a lot of communication between the manned aircraft pilots with the unmanned drone operators about the airspace usage. And naturally, all of these, they are located in the same space physically in the control center and interact with each other constantly through verbal means and visual means and so on. Yeah, this is a bit more on practical level, the phases that would be followed by those operators in conducting this kind of a drone swarm operation in wildfire situations. So first, they would plan the operation and define the aims and also the limitations and the boundary conditions for the swarm operation. Then secondly, they would configure the drones for the operation. And third, they would take the drones to the launch site. And then they would be launched and they would supervise the progression of the operation. And obviously, then when the real-time results come in, they would interpret them and send them forward to relevant stakeholders and maybe react to them accordingly. And they would also respond to some unexpected events. Obviously, these are very dynamic events, so they might have to possibly intervene with the flying of the drone swarm when necessary. And finally, once the mission is accomplished, then they would have to do the ending of the operation. Yeah, I don't go into this system interface perspective that much. My background is in user interface design, so I'm looking also from this perspective things, but basically there should be an intuitive, easy to use tool on an abstract level enough so that the individual drones would not be needed to be controlled or micromanaged, operated, but they would be just following like high-level inputs, like let's say survey this area on the map by painting the area, and the autonomous swarm would take care of the rest. And yeah, but for the sake of time, maybe I will skip this example because here is where this ConOps gets interesting. So we will have here the relevant actors and their interaction channels, and this is sort of the socio-technical system in a diagram format in one page. So let's say we have the human operators. Well, this is human factors engineering approach. So the human operators are in the center there in a command, control, and communications place where they are located. And of course, there's some other relevant actors there on the left. You can see the fire incident commander, the fire crews, and authorities, etc., etc. And
brigades.
Yep, and these other actors will have different types of information or task requests to the human operators in the C3 center. And naturally, what is possible to be given to them and done by the human operators is dependent on the operational environment and its characteristics, like the extent of the fire area, the weather conditions, the features of the terrain, and all of that. So then the human operators are obviously conducting the planning, the supervision, and control of the swarm operation based on these different demands that they have to handle. And then the semi-autonomous quadcopter swarm, when it is airborne, it receives this kind of unprocessed situation awareness and other data from the target environment, which is collected by the sensors of the swarm's drone units, and then conducts sort of like a sensor fusion to combine the information into meaningful wholes. And based on the actual situation, there are these kind of different use cases, user requirements, task goals, situations, and scenarios that are related. When they analyze this data in the communication center, and also from the semi-autonomous drone swarm that is flying in the air, obviously data about the status of the swarm and its members can be received as well. So anyway, and this situation awareness information will be then refined to the incident commander by the data analyst and C3 center, and the incident commander and other stakeholders, well, they can also receive this unprocessed data directly from the swarm units, but that might not be as useful as process information because their time is of essence here, really. And I didn't mention there on the right, you would have different types of things like level of automation, technical platforms, data communications involved, along with this appropriate airspace management for use-based solutions. But let's not go into those here. Basically, this is in one diagram, the high-level future ConOps for operating a drone swarm when a forest fire situation is occurring. So in practice, FireMan ConOps. Now, finally, some discussion and conclusions about this study. So first of all, swarm-based drone operations seem to offer a really attractive approach for wildfire management, and especially for the detection and monitoring parts of those fires. And this is basically because the use of drone swarms could enable a really fast mapping of a large area and more comprehensive situation awareness and efficient coordination of rescue team resources. And then as a general point, when designing drone swarms for wildfire management, also the human factors aspects really need to be carefully addressed in addition to the technical aspects. And also, well, similar drone swarm ConOps that the one that we have here could be developed for other types of surveillance and monitoring missions than wildfire. Well, basically everything which requires surveying of large terrestrial areas, such as search and rescue, or I would say military reconnaissance missions. And yeah, as you know, it's just a matter of teaching the machine vision and the AI algorithms of the drone swarm sensors to what to detect in the environment. So yeah, this very scalable system, I would say. And in general, I would say that we found that this ConOps approach is really a useful approach and works nicely, sort of like a boundary object for all the stakeholders in the design of a complex socio-technical system when these kind of different requirements are needed to be assimilated. And yeah, finally, in practice, in this future work in the FireMan project that will focus specifically on the refinement and implementation of these ConOps into more practical solutions, such as the swarming algorithms that we have been developing, the simulations, the AI solutions for the detection of the fire and smoke, and also to maybe even to practical operational procedures for the fire brigades for different wildfire situations. Yeah, and well, I have to say, of course, one of our aims is to scale these solutions then to other places than Finland, where, well, into those places where wildfires are really a huge problem, like, you know, for example, in California, Southern Europe, or Australia. So the summer is just starting, and let's see what kind of things will happen in these areas. So that's it actually on my behalf. There's my contact info also for later discussions, but please, by all means, well, send me a connection request in LinkedIn or somewhere. I post quite regularly there about various drone related things, but for now, I would thank on my behalf for your attention. And Fabrice, maybe you could take over the screen and show some of the slides and simulations that we have done in this FireMan project. Okay.
Sure. Do we want to go to my presentation, or maybe there is a urgent question for Hannu first from the audience? If none, then I will share my screen.
Okay.
Right. Okay. So first I'll share my own video feed. So hello everyone. So I'll just quickly introduce myself. My name is Fabrice Saffre. I'm a research professor for autonomous mobility systems at VTT. I have been living in Finland for about 4 years, but as you can probably tell, I'm not Finnish. I am actually from Belgium, Brussels. And before I came to work for VTT, I was chief researcher in British Telecom in the UK for almost 20 years. My background is actually quite exotic because I did my PhD in theoretical biology in a physical chemistry labs in Brussels, and my area of expertise is actually collective intelligence. That's the connection with swarms. So what I've been doing for my entire professional life after I finished my PhD is trying to apply nature-inspired collective intelligence design principles to information systems in general, so information communication technology while I was in the telco industry, and now more specifically cyber physical systems in mobile application and mobile robotics. So without further ado, I'm going to try to share my screen. Which one? It seems like I have to share individual applications, so I'll do that. Right, so this is basically immediately following up from what Hannu has been showing you. Can you see my simulation window now?
Yes, we can see that.
Okay, because I cannot see it bizarrely on my Zoom window. So basically, this is meant to illustrate how we would develop swarm algorithms to perform an autonomous cordoning maneuver around propagating fire. So if I start a fire in the middle here, it will gradually propagate through the environment, and of course the rule should be, I mean, the objective is to detect that event as soon as possible and then to coordinate so that you can monitor its progression from all possible fronts. So now I just started the fire and it's probably already out of control, so I will just reset it just to show you how the fire propagates. You can also add a bias in the form of wind blowing. So in this case, the wind is blowing from the northwest to the southeast, and so you will see that it will start propagating more towards the bottom right of the screen. So that is just the fire simulation itself. But if I reset the forest, and now what I do is I introduce some patrolling drones here in this environment, so that basically they can monitor the environment that they've been tasked with protecting from fires. And at the moment there's no fire, so they just follow this kind of random exploration strategy with some biases so that they don't duplicate efforts too much. So in essence, they bounce over each other and they bounce over the perimeter of that box in which they live. Now, if I start a new fire here, eventually one of these drones is going to detect it, and then it will start recruiting other drones to come to its rescue and start forming a perimeter around it. This is what's happening right now. So at the moment, they are finding the perimeter around it, but as the fire propagates, of course, it becomes more difficult to follow it from all possible direction. But because we are using a collective intelligence framework as opposed to a script, it means that the system is able to use whatever resources you throw at it to restore the complete circle around the fire for as long as possible. Now, with the current parameter values, this is as best as they can do because I cannot go more than 12 drones in the system. But as you see, they still distribute themselves more or less homogeneously around the event, and that means that they would be able to continue providing up-to-date real-time information to the firefighters who would be tasked with controlling the event. As Hannu mentioned, at the moment, there is very little real prospect of the drones being able to control the fire by themselves because of their limited payload. So they are essentially a situational awareness technology. That's how they envisage at the moment. So that was the demo that I showed back in TUD that resulted in us being invited to present to you guys tonight. But now I want to switch to a different thing, which is the presentation I gave at the International Wildfire Conference in Porto just last week. So that means I have to share another window. Bear with me. So you should now see my, oops. You should now see my title slide. Right, so this is basically a presentation about research that is currently in progress about using multiple types of drone platforms in complementary roles for environmental monitoring. This is work that is being done here in VTT by myself, Hannu, and Jukka Sassi, but also in collaboration with our colleague Hanno Hildman from TNO, who is also based in the Netherlands. All right, so the challenge that we're having in terms of combining these multiple platforms is that at the moment, of course, we already use many different types of sensors in detecting and monitoring wildfires. These go from satellites to fixed sensor platforms on, for instance, on towers in the environment, on the top of hills and stuff like that, all the way through aircraft and potentially usually remote controlled drones. But most of the studies that you see seem to focus on one platform or the other. And when they are combined, they are usually combined very much in an ad hoc fashion. Essentially, it means that whatever is available once the fire is detected is being mobilized to monitor the event. But we think that this kind of ad hoc opportunistic approach is suboptimal. So we try to formulate concepts of operation that would allow us to combine these platforms and be able to capitalize on their strength and compensate for each other's weaknesses in a more principled way. And we think that this has huge potential for a number of applications, not just the control of wildfires, but also all sorts of missions that involve exploration and monitoring. And this is especially true if you're talking about autonomous platforms, because in this case, very often you want to be able to count on their ability to self-organize and perform the mission with as limited human input as possible. Now, in this presentation, we're just presenting a method to actually try to find a way to design the right fleet of different types of aircraft in order to perform a wildfire monitoring mission. So in the scenario that we've chosen to illustrate this, we have two types of drones. One is a fixed wing aircraft and the other one is a quadcopter. So the fixed wing operates at high altitude. It flies very fast. It flies for a long time. It's very energy efficient. It carries sensors that cover a large area, but it's also very expensive. The quadcopters, on the other hand, they operate at lower altitude. They are much slower. They have a shorter range. The field of view is also smaller, just because they cannot see the other side of the hill. But they are cheap. Let's say that there is a factor 8 between them. So what we've done is we've tried to combine different numbers of these two platforms and see which ones would give us the best results in terms of the ability to detect and disambiguate potential heat sources. Because as Hannu mentioned, one of the key problems that they have when trying to locate and determine the severity of a fire event is that you might have many false positives, in the sense that you might spot a barbecue or a controlled event that actually doesn't represent any danger. And when I was at the conference, I actually saw a presentation that suggests that, for instance, in California, they already classify different fires that are all real fires, but they still have severity levels that are graduated from 1 to 5. And of course, you want to be able to determine as early as possible whether one particular start of a fire is going to turn into a problem or if it's going to burn itself out. Now, the question that we are trying to solve, of course, is there is a kind of trade-off between detection and disambiguation. So a fixed wing flight at an altitude allows it to detect possible fire events at a long range. So for instance, in the simulation was 3 kilometers. while the quadcopters, they only see in a small cell, 500-meter radius. Now, what we've done in the simulation is that we populated it with a fixed number of events, which are true and false positives. And disambiguation and detection are executed separately using different probabilities that depend on the distance at which the event is observed. I don't want to go into the details here, the equation at the bottom here, but in essence, what happens is that it's very likely that a fixed wing aircraft will be able to detect a possible event, but it is unlikely to be able to determine whether it's a false or true positives. On the other hand, a quadcopter, once it is in close proximity to the event, will be able to almost quasi-deterministically being able to do the correct assessment of its severity. On the other hand, if you only have quadcopters, it's very likely that you will miss some events because you don't have the scope that you would have with the fixed wing aircraft. So in terms of the way that these two platforms cooperate, it's relatively straightforward to understand. You would have the fixed wing aircraft flying at altitude. When they detect a possible fire event, they will fire a request for a disambiguation mission to be flown by a quadcopter. The quadcopter will then go to the location that has been determined as a possible fire event by the fixed wing aircraft, and then upon reaching the site of the event, it will be able to either classify it as a false positive, in which case no further action is needed, or as a true positive, in which case you will be able to trigger a response by the appropriate actuators, whether they are, for instance, terrestrial drones that can carry a large amount of water or fire retardant to the site, or human firefighters. Now, the result of our simulations showed the effect of this trade-off. So we tested multiple fleets. We assumed that we had a fixed budget of 160k euros, which amounts to 2 fixed wing aircraft, or 16 quadcopters, or 1 fixed wing and 8 quadcopters. And we didn't consider operational costs, we only considered the CapEx. So the results have emphasized the advantages and disadvantages of both approach, and actually emphasized the advantage of using the hybrid fleet over the two fleet that only feature one type of UAS. And this is illustrated in the two graphs. I don't know if you can see my cursor here, but on the left-hand side, this is a survival curve representation of the ability to detect events. So it's a number of events that remain undetected as a function of time. And the three curves correspond to the three types of fleet. So lower is better, of course, because that means that you detect them faster. So this one is for the top one is for the quadcopters only. The continuous black line is for the 2 fixed wing, and the dotted one in between is for the hybrid fleet. And here, as you can see, you have just the linear progression here between the three. So the one that performs the worst is the quadcopter, because they can only cover so much space in so much time, and therefore many events remain undetected for a long time. On the other hand, if you have only 2 fixed wings, then your ability to detect the events is maximized because they can cover a lot of space in little time, and in between you have this intermediate signature. But what's interesting is if you compare this with the number of events that remain uncategorized, so you don't know if they're a false or a true positive, you can see that you have a flip between the hybrid fleet and the monomorphic fleet that contains only the 2 quadcopters, the 2 fixed wing aircraft. So this indicates that if you have a mix of quadcopters and fixed wing aircraft, you actually are in a situation where you may not detect fire events as efficiently as if you invest your entire budget into fixed wing, but you will be able to disambiguate and allocate your firefighting resources more efficiently. So this is, in our opinion, the best illustration of why there is a need for hybrid platforms in wildfire detection and monitoring. So basically, conclusions about that is that numerical experiments provide evidence that a hybrid fleet has significant advantages if you consider the need to eliminate false positives. Basically, the method that we've presented here is able to determine what would be the best mix given arbitrary budget constraints once you give them the characteristics of the platforms that you are considering as a possible candidate for acquisition. Now, we also tested other intermediate types of UAS, so there's no reason why you can use only 2 types, but this is just for illustration purposes. But I didn't present the results that involve other platforms, but you can basically test whatever number of platforms you want, and the simulation study will automatically generate the fleet that has that gives you the biggest bang for your buck, essentially. Now, I wanted to show you one last thing before I finish. I see there is someone in the chat saying something. I don't know if it's a question. No, it's just someone has to leave. So I'll show you my my other demo, which is really work in progress. It's so much work in progress that even Hannu hasn't seen this because I've done this in the last 2 days. So let me again change which. Oops. Stop share and start share again. Seems like every time I have to share again. So you should now see, do you see a big white screen with, no, not yet. No, you see it.
No, yeah.
No, you see it. So basically, this is because we realize, and I think I mentioned that at the very beginning of my presentation, there is the wildfire monitoring example is but one example of a great many different types of mission that could use similar solutions. And so I wanted to abstract from that and give you an illustration of, in a general case, when the target is any kind of event. It could be, you know, a victim in a natural disaster, or it could be, you know, a dangerous soldier in an invading force, or it could basically be anything. You need to have this balance between detection and you know, whatever action you need to take in terms of being able to deal with this event. So for instance, you might be noticing that there is a victim that is lying down on this area in the rubble, but that doesn't help that victim. You need to send someone there to help them out. So that is what I'm trying to look at here. So all of these little target circles with a question mark associated with them are events that we know about because it's a simulation, and I have a bird's eye view, but the system doesn't. And then I can actually mix again, like in the presentation I just gave, different type of aircraft, of unmanned aircraft, to explore this. So we have a fixed wing aircraft here, and we have a quadcopter, like an example here. Now, for instance, if I only have fixed wing, then they will be able to cover a lot of space, but they won't be able to fly close enough to, I mean, statistically, they will find it more difficult to fly close enough to one of these events to actually be able to classify it, to categorize it convincingly. So here, for instance, I'm going to speed that up. So this one, you see, detect and then flies towards it. So as long as it can fly towards it, very often it will be able to fly close enough that it can actually take action to do something about it. But of course, there will be cases in which its turning radius, because it's a fixed wing aircraft, will mean that it's unable to actually reach that target. So I'm waiting for that to happen. I don't know if it will happen. Maybe if I put more than one of them, it will help. And so eventually one of them will get trapped around that event that is trying to reach and it cannot reach. Okay, of course, it's not happening. Yeah, this one is being trapped here, for instance. And of course, that means that you could, of course, detect that it is trapped and solve that problem. But another thing that you could do is actually start to combine multiple type of aircraft and make sure that you get the most of what they're good at. So, for instance, the fixed wing are good at detecting, they're not good at acting. And the quadcopters are not good at detecting because they fly slowly and they fly close to the ground, so they don't see very far, but they're very good at acting because they can essentially turn on a dime. So this is what I'm doing now. So I'm going to add some quadcopters, and now what happens is that now basically these ones are no longer even trying to come close. When they detect, they just carry on and they just report that they've detected something. And now, of course, that means that the quadcopters are the ones who are performing the heavy lifting, if you want, because once the event has been detected, the nearest quadcopter is being dispatched to the location. And so that means that the fixed wing aircraft can focus on what they do best, which is to cover a lot of space in as little time as possible. And so now you have this kind of best of both worlds scenario, if you want. And of course, we're still working on the algorithms to optimize this, which has not been done. As I said, this is work in progress. But I've again started doing simulations to try to determine what is the best combination. So imagine that one of these fixed wing costs 100,000 euros and one of these quadcopters costs only 10,000 euros, which is ballpark figure accurate. That means that, of course, what do you gain by adding a fourth fixed wing aircraft? Why do you gain by adding another 10 quadcopters? And this is, of course, all depends on the density of target, the area under surveillance, and et cetera, et cetera. But basically, you need to be able to determine in whatever, for whatever parameter values, what is the optimum fleet to perform the mission, depending on the characteristics of the mission and the characteristics of the environment. And I think I'll stop here because we're closing the hour now. And if there are questions, I think Hannu and I can take them simultaneously. I will leave it running in the background.
Thank you very much. Interesting, very interesting work again. Let's see from the audience. Are there any questions from the audience? I can start with the first question. What do we need to do in order to see such concepts implemented in reality?
Hannu, do you want to take that first?
Yeah, I can start and you can continue. So basically, we need to have a lot of, I would say, regulatory advancements. That's one key area that is now restricting certain type of operations. And of course, some technical advancements as well, but I think the technical side is, I would say, in a pretty good shape already. Maybe the connectivity might not be very good if we talk about cellular connectivity in wilderness areas. So if we have wildfire in the middle of nowhere here in Finland, probably the connectivity is not that good that you could stream a very detailed resolution, a good resolution video feed out of there. But yeah, that's one area as well. But maybe the satellite connectivity will solve also some of those problems. Yeah, and of course, I have to mention that we have to fit all these solutions to the actual human work that is conducted. So we need to really study how the humans are using the system and design the systems as user-friendly as possible based on the needs of the users. So those are some of those things, but maybe Fabrice, you can continue.
Well, I think you've covered the bases here. I think the main problem, as you say, is regulatory. For instance, at the moment, we have a lot of regulations that forces you, well, that limits what you can do beyond line of sight. There are some hard constraints on basically being able to use autonomous platforms. In most cases, you have to have a human pilot, at least on standby, to be able to take over if something goes wrong, which of course limits the ability to use these autonomous swarm solutions. One other aspect that would need to be addressed, and I think you mentioned that in your presentation, Hannu, is the interface between users and swarms. So at the moment, the problem is that very few people are trained to use swarms. Many people are trained to use individual drone platforms as remote controlled sensor platforms, essentially. But the best use of a swarm implies that you're able to give the collective a kind of abstract description of the mission. It might be, as Hannu mentioned, just go and perform a reconnaissance in this area of the map, or it might actually be something as simple as abandon the current mission and refocus on something else. And then the system should be able to, if it's designed properly, but that's what we're working on, it should be able to respond to this sort of changing priorities by the end user. And as long as the end user is able to express what they want the swarm to do in the right way, then all of the minutiae of organizing the mission should be left to the swarm. But I'd say that the combination of regulation and effectively lack of training in using autonomous platforms is the main challenge.
Thank you. Yes, Alex has a question in the chat. Do you see it?
Yeah, I see it. So the sensors.
I have to stop sharing, I think, to see the question.
The sensors that would be ideal for the firefighting use case is a very good question. I would say that the thermal imaging cameras are definitely one key sensor. We have noticed that you can see through the smoke and you can see the fire front advancing. So that is very relevant information for the fire incident commander. But there are also some other type of sensors than cameras. Obviously, different kind of, I would say, ultraviolet detection systems, or this kind of very, I would say, detailed radars could be utilized to monitor the airspace as well. And I don't know, Fabrice, do you have any other sensors in mind?
No, because I'm a theoretician. However, and for me, a sensor is something that detects the event that I'm designing algorithms to track. But while I was at the conference in Porto, there were a lot of people who were presenting new hardware for fire detection and monitoring. So it's an active area of research. I remember that I was looking away from the screen because I was reaching for a business card I grabbed there from a startup in Finland that is called Fenno Orum. And these guys are developing a new kind of sensors that seems to operate neither in thermal part of the spectrum nor in the visual part, but in yet another part. And so there is obviously an active research field to try to determine what is the best way to actually look through all the various types of noise that might affect the sensors that we used to work with, which is basically as we discussed, the visual spectrum and thermal imaging.
Yeah, and of course, maybe some sort of gas detection or this kind of smoke detection is something that could be really useful for a wildfire sensor. So yeah, these kind of things probably.
I was wondering, Fabrice, in those simulations, do you take atmosphere conditions and I don't know, winds, climate into account? How are operating drones in those kind of environments?
All right. So in the final simulation that I showed, no. We are not, in this one, it's not yet implemented, basically. In most cases, what we've done is we've actually used wind in the sense of a laminar flow that would actually increase the energy expenditure and reduce the speed when you are going upwind and vice versa. So this is as far as we've gone. Now, in general, this doesn't really affect the collective intelligence aspect. It affects the performance of the swarm. So, for instance, if you are in the case of a fire that is propagating in the direction in the southwestern direction, as I shown, southeastern direction, and you happen to be starting at the wrong side of the fire, you may have to fly against the wind in order to be able to complete the encirclement maneuver, which will of course reduce the time you can spend airborne and potentially reduce your chances of actually achieving that cordon. But basically, we are using some very basic atmospheric condition parameters, but nothing detailed. So we're just trying to test essentially the robustness of the algorithms that we develop to these kind of effects, but by taking them on a relatively simplistic level.
Yes, thank you. Thank you. I see that people are dropping, and if there are no questions, I would like to thank you both again that you came at this hour late in the evening. And please stay in the group and keep in touch, and let's see how it's going to be and when are we going to see those new concepts. So thank you very much again, Hannu and Fabrice, and see you in the next meetings.
Thank you for the invitation, and thank you for your questions.
Yes,
Thank you.
For the